In this presentation, we're going to discuss reactions of the side chains of benzene. Our first reaction is benzylic halogenation of the side chain. You first see this reaction in OChem 1 when you learn about radical reactions. So in the example shown below, you start off with toluene, add in molecular chlorine with heat or light as a catalyst, and if you control your equivalence of chlorine, you will end up with mostly a single halogenation in the benzylic position. However, controlling this reaction is pretty challenging and you mostly end up with a mix of products. So as you add in more chlorine, you're more likely to end up with polysubstitutions. If you would like to control the halogenation, using N-bromosuccinimide or NBS is a better way to do it. Using NBS and dialkyl peroxide or light, you can actually put a single bromo group onto the benzylic position. And this is really valuable because then you can do further reactions at the benzylic position, such as reacting with sodium ethoxide and doing an SN2 reaction in order to create an ether. If you are doing an elimination reaction with a benzylic side chain, you have to consider that some potential products may be conjugated, whereas others are not. And the conjugated products will be favored because they are more stable. So remember that when you have those overlapping unhybridized p orbitals, as we would here, that's going to stabilize the product and make it the major product. Whereas the non-conjugated with the isolated double bond will be the minor product. So in this example, we have an alcohol where the alcohol is actually in the position next to the benzylic position, and it is being dehydrated with a catalytic amount of acid and heat. If you are to do an E2 reaction, you're also going to have to consider that the conjugated product is more likely to be favored than the non-conjugated product. And this example also has the added layer of the fact that the conjugated product is major and also is the more substituted alkene versus the isolated alkene, which is less substituted. So there's a couple different reasons here why in this particular example, the major product is the major product. We can also do additions to the carbon-carbon double bond of alkenyl benzenes. In this top reaction, we have hydrobromic acid, and we do have a conjugated system. However, previously we saw with conjugated systems that 1,4 addition is a possibility. You're not going to be able to pull off a 1,4 addition in this situation because one of those carbons is going to be aromatic. So that's not going to be something that we consider here. Instead, what we have to consider is that this is going to be a Markovnikov addition, and we are only concerned about this double bond. So remembering that the first step of a Markovnikov addition to a double bond is protonation of the alkene, we have to keep in mind that the hydrogen is going to go on the less substituted, or in this case, the less stable carbon, because that gives us the carbocation in the benzylic position, which is not more substituted than the other position, but is more stable because it's going to have resonance with the benzene ring. So in this situation, the substitution is not actually the issue, it's the more stable carbocation that is the issue. And then by adding in bromide, you end up with your final product, which adds a bromine in the benzylic position, and remember that hydrogen is still there, but it's implied, so we do not need to draw it out. In the second example, we have HBr, but we also have peroxides, so this is indicating an anti-Markovnikov reaction. Hopefully you recall that the anti-Markovnikov product is going to go through the more stable radical, and this is going to give us, in a normal anti-Markovnikov situation, the less substituted bromine, but in this case, it's just not going to be in the benzylic position, it's going to be in the neighboring position. So our radical Remember, we are going to start with hydrobromic acid and peroxides. Through an initiation step, we're going to create bromine radical, which will then react with our alkene. To give us the benzylic radical, which will then be terminated to give us our product. So the key thing here is that the anti-Markovnikov reaction wants to go through the benzylic radical, while the Markovnikov reaction wants to go through the benzylic carbocation. Our next reaction is the oxidation of the side chain. So what you might recall from previous uses of these reagents is that if you have something like a primary alcohol and you react with these same conditions or another strong oxidant, you'll end up with a carboxylic acid. Or if you react with a secondary alcohol, you would end up with a ketone. If you react with a tertiary alcohol, you get no reaction. And the reason that that did not react is because it did not have the 100% necessary hydrogens on the carbon that was attached to the oxygen. So our rules actually continue to apply here when we were looking at alkyl side chains and oxidation with potassium permanganate. So in this first example, we have toluene. We're reacting with potassium permanganate and we end up with benzoic acid. Note that there is not an oxygen attached to this starting material. So it's not the presence of the oxygen that matters here. It's the presence of the benzylic hydrogen. But what's really interesting about this reaction is that even though this has an ethyl group, we still have these two hydrogens here, and when exposed to the same reaction conditions, this will also make benzoic acid. So will this. And then our bottom one, not having a hydrogen, will not react. So this follows all the same rules, but it does something kind of bizarre where we are cleaving the bonds to other carbons and they kind of get obliterated. So what's really cool about this is that no matter what that carbon side chain looks like, as long as you have one hydrogen in the benzylic position, this side chain could be the craziest thing in the whole world. You could have so many things going on. It's all going to get obliterated and get turned into benzoic acid. This next part is a little different because it's not actually the presence of the hydrogen that matters. In our first example here, we do have a hydrogen in the benzylic position and we end up with benzoic acid. But that's not actually what's causing this to work, because note in our next structure, there is no hydrogen in the benzylic position. But when exposed to the same conditions, you get benzoic acid. Same with the ketone, acetophenone. There is no hydrogen in the benzylic position, but it still makes benzoic acid. So here, this is more related to the cleaving of a double bond. In this situation, you have to have at least one unhybridized p orbital on that carbon in order for this reaction to occur. So we are looking for pi bonds attached to the benzylic carbon. Now this last reaction is really wild. This is oxidation of the benzene ring. So when you react an aromatic compound that has some sort of alkyl R group with ozone, acetic acid, and hydrogen peroxide, you will end up with a carboxylic acid. But notice this is not benzoic acid. This actually retains the R group from our previous structure to create a carboxylic acid. So if we were to react in butyl benzene with the same reaction conditions, ozone, acetic acid, followed by hydrogen peroxide, we would end up with butanoic acid.